Welcome students. Today we're going to talk about what connects these objects, if you want to call one direction an object, and the fact that phones can flip when you reorientate them, and the somewhat gruesome world of hunting. It's physics, of course, and we're going to talk about how kinematics joins them. So this is a pretty typical acceleration problem, one where we're going to use the acceleration equation that we've used already. Ball comes in, hits a racket, and accelerates in the opposite direction. Clearly there would be quite a big acceleration involved. The equation that we've used before is A is equal to V2 minus V1, or the change in velocity, over time. So that is what acceleration is defined as. And pretty straightforward equation, but it is important to note that acceleration and velocity are vector quantities. So we really should give these values a directional component. How do we do that in physics? Normally with a plot positive or negative. So we're going to set north and east as positive. We don't have to. You can set them as negative as long as you set west and south as the opposite. So in this case, west and south are negative. So this is important because if you don't use the right values and the right sign value, you will get the wrong answer. So acceleration is V2 we've defined as a negative 7.3 meters per second because we set westerly direction as a negative. And we're going to take away that positive value of 6.0 meters per second because easterly is positive. And we're going to put it over the time value. So how long was that acceleration acting for? Well, we're going to pull it out from the statement above, which was 0.094 seconds. So we're going to get a bigger value for that change in velocity. And that should make sense, 13.3 meters per second. We're saying that the acceleration was in the negative direction because it moved the ball in the westerly direction. And you would get quite a high value for acceleration. So this is introducing the component of direction because remember we are talking about vector quantities. Okay, so kinematics. We talked about the different motion graphs, how you get from one to the other. A very important point at this moment is the basic kinematics equation for velocity of displacement over time can only be used when there's no acceleration. This is an average value and it can only be used when there is no acceleration, in other words, uniform velocity. So what about when there is acceleration, which is a little bit more real world, I guess. When acceleration is present, as happened many times in the world, when acceleration is present, you need the big five. What are the big five? Well, they're a set of kinematics equations that we're going to talk about today. So the big five, well, they're not, if you're in Canada, you might think that they're banks, but no, they're not. They were a set of animals that were prized by hunters in the past. Maybe you can stop the video and try to figure out what those animals are. The big five are shown on screen, but in the physics kinematics world, the big five represent a set of kinematics equations that will allow us to figure out variables. So the very first one is Vf is equal to Vi plus At. Now this is a very clear reworking of the equation we just showed in the last slide. So A is equal to Vf minus Vi, or final velocity minus initial velocity over t. Now if we rearrange that algebraically, and we move the t above the line, and we bring the negative Vi across to the other side, we can get a description for Vf. We can get an equation for Vf which is equal to what's commonly the first big five equation. So this is one which you might use when figuring out Vf or Vi. Second equation is when we need to get the displacement. So remember, the displacement on a Vt graph is the area under the curve. The green portion is V times t, the rectangular portion. The red portion is derived from a half base times height. If we know that the base is t, and we know that the vertical point here on the triangle is equal to AT, then we can reorder that and call it a half AT squared. That is a half BH, or the area of the triangle. and then we can put it into the equation. So it turns out that we can derive the second equation. There's three other equations which are very useful. Will I ever ask you to memorize these equations? Absolutely not. You can use a big 5 equation sheet, and it's just a matter of practicing these 5 equations. And it is very important to try to understand which equation you would use for different scenarios. So these are the big 5s. You'll notice that there's different variables involved in them. Sometimes it's more beneficial to use equation number 1, and sometimes equation 2 or 3, and it would depend on what variables you've been given. So for example, if you were using, depending on the variables that you've been given, if you were given variables, you were given enough variables and you wanted to figure out what delta D was, you might use equation number 3. However, you would only use equation number 3 knowing that you have no V2 value. So here's a practice for this. Vivian Velo, a female racing driver, reached a speed of 628 kilometers per hour from rest in 3.72 seconds. How far did she travel in that time? First thing we need to do is to convert kilometers per hour to meters per second, which we've shown how to do already in class, and we get 174 meters per second. It is important to note here that there's 3 significant figures, so don't forget those. That's what was in the question at the beginning, so that's what we've got to stick to, the least number of significant digits. How do we solve this problem? Well, we use what's commonly referred to as the GRASP method, or the GRASP method, whichever you want to call it. I'm okay with that. So you start by pulling out from the question, what was I given? Well, you were given the final velocity, 172 meters per second. The initial velocity is 0 meters per second because the car driver started from 0 meters per second. And the change in time is 3.72 seconds. Sometimes students won't notice that V1 is 0 meters per second, but she reached the speed of that from rest, and that's the key here. What are we trying to figure out? Well, the required value, or the required, is delta D, the displacement. How far did Vivian Velo travel? The next section in the GRASP is A, which is the analysis. So how do we figure it out? It's just about writing out what we use, the tools we use. And we're going to use the big 5. So we're looking for delta D. We have V1, we have V2, we have T. So which equation would be best to use? Well, in this instance, it's equation 2. The other equations simply wouldn't be great ones to use because you don't have A. So we're going to use the correct equation, which is equation number 2 in your big 5 sheet. And you're going to isolate and try to determine and calculate the variable that you need. So pretty straightforward. From this point on, it's a little bit of plug and play. And you have V1, have V2, and have delta D. Sometimes you'll have to use one equation to get a value in another equation. You'll have to use 2 of the equations, but you will always be able to use the big 5 to determine the values that you require. So we put in the values. V1 was 0 meters per second. V2 was 174 as we converted earlier. And Vivian Velo takes 3.72 seconds to reach this colossal velocity, or speed in this case, because there's no direction. So how far did Vivian Velo go? Well, you would have to work that out, not forgetting that there's a half in front of everything. And by my calculations, although I stand corrected, it's 323 meters. So this is a displacement value, how far they've traveled, 323.64 meters. How can we confirm that? Well, the seconds value should have cancelled, leaving you with meters. Remember, the units can cancel, and that's always a good way of double checking. You've got the correct units. So the final thing you would do in the GRASP method is the P, which is paraphrase. Sometimes you will have seen this as a GRAS, in which case the final portion is a statement. So the 323.64, we want to write that using the correct number of significant digits. So we're going to say 324 rounding up for 3 significant digits. So our paraphrase at the end, we write out our answer. Velo traveled 324 meters in this time. Okay, that's quite an achievement, but she is in a race car and she is moving at a serious rate. Okay, next question that you can work on. So that's a work question for you. The next one you can work on is this one that's on the board right now. A bullet is moving with a speed of 367 meters per second when it embeds into a lump of moist clay. This is old school. They used to test bullets by doing this method. The bullet penetrates for a distance of 0.0621 meters. So that's how far the bullet embeds or goes into the clay before it's stopped by the stopping force of the clay. Determine the acceleration of the bullet while moving into the clay. A couple of things here. You should realize that the acceleration is in the opposite direction of velocity. So if the velocity to the right is positive, acceleration should be negative. If the displacement to the right was positive value, as you've seen on screen, and the velocity was positive, then that acceleration value to slow it down must be to the left, and that should be a negative value. So you should be expecting a negative. So you can practice using the big 5, and please practice this one yourself. Remember what's required. The acceleration is what's required, so this value should be in meters per second squared. Figure out which one of the big 5 you're going to use first, then use that to solve, so step by step, and then paraphrase. So write out the values that you've got, the givens, as I've done. Write out your required, use your big 5, and then paraphrase. Okay, so find out which one of these big 5 fits. Okay, so one of those big 5s will work for you, and this time you're trying to figure out the acceleration value. Okay, so now you've seen a worked problem, you've done a work problem, and now it's your turn. So work individually on the problem that I've given you. You can also work on the problems below as extra problems. I would also like you to come up with your own problem. So you can go online and find one, or you can devise your own problem based on the variables we've talked about. And we're going to talk about your problems in class, where we're going to practice those problems tomorrow.